Thank you so much for your clever answers. For the next group, please come over. Our next topic will be on the design and validation of whiplash injury prevention system by Mr. Radwan and Mr. Harris.
Okay, Assalamu alaikum wa rahmatullahi wa barakatuh. I'm Abdullah Radwan and my colleague Abdullah Harris. Today we'll be presenting our summary of the senior project, the design and validation of whiplash injury prevention system. We'll set off from here with an introduction to the whiplash injury, where we'll talk next about the definition of the problem statement and the objectives of the study. And then we'll move on to our methodology, results, and we'll finally conclude in the end of the presentation. I'll leave the mic now to my colleague Abdullah Harris to start, so please sit back and relax and enjoy.
Okay. Good morning, everyone. So let me start with the definition of what is whiplash. Whiplash is a term used to describe a neck injury related to sudden distortion of the neck. It is enough to know that in the period between 2001 and 2006 in Qatar, the number of people suffered from head and neck injury due car collisions were about 6,700. And with the inflation of population number here in Qatar, we can imagine how big is this number right now. And in large countries such as United States, there is 800,000 whiplash injury in 2014, and this cost the government there around $5.2 billion. Researchers found that the main reason for whiplash injury is back rear impact. So we are dealing with a big problem. What are the solutions to this problem? Before moving to solution, we will describe the mechanism of occurring. Whiplash has a mechanism of 3 phases. The first phase when the seat strikes the driver and the torso starts to accelerate. However, the head tends to keep its position. In the second phase, the head accelerates backward with causing a hyperextension to the neck, and this is causing a damage to the frontal soft tissues of the neck. And in the third phase, it's the rebound phase, with the torso moving forward and the seat belt catching the torso, which will make, again, a compression to the neck. So, how are the solutions to this problem are rated? One of the widely used methods for rating head restraint is IIHS method, which gives a rating out of 4 to the head restraint: good, acceptable, moderate, and poor. And an example from our streets that we saw and widely used in Qatar is well, which is head restraint proposed by Toyota. They claim that this solution to the problem will hug the driver during the back rear impact. But however, many types and models of Toyota cars got poor rating head restraints. So our main of this study is to limit the dynamic response that leading to whiplash injury and designing a whiplash injury prevention system and validating the proposed solution. So our journey reaching the final solution, starting from concept generation, passes through different stations of analysis and finally reaching the proposed design. The validation the equation or the criterion used for the validation is NIC, neck injury criterion. It's related to the relative acceleration between the last vertebrae of the neck and the head. This is the proposed design. 2 sliders which limiting the response, movement, and the results, and how are these elements effectively reducing the whiplash injury with my colleague Abdullah.
Thank you, Harris. Okay, to start off from here, we start with the preliminary stages of simulation to test the functionality of the sliding motion. So with that, we use the simplified model of the human body, which is the hybrid 3. And then we moved on to, we opted to, for a more detailed model of the human body, the total human model for safety thumbs, which is by Toyota Corporation. We used LS-DYNA pre-post software for the modeling, and we used the simulation environment of ANSYS Multiphysics using the LS-DYNA finite element code. In these preliminary stages of simulation, the first condition that we had was a fixed condition to obtain an average knowledge on the normal impact accelerations during gradient impact, which reached up to 6.5 g, as seen from the slides. And with activation of the sliding motion, we can see that the maximum impact load acceleration reduced to a minimum of 1.5 times the gravity acceleration, which resembles effective minimizing of the dynamic response of the human body during impact. Now, to test for the head restraint deployment, we had to modify the seat according to what other people have been doing in the engineering and scientific community. And for that, we had two tests that we have to do. The first test is the head restraint deployment through reduction of the backrest distance of the head restraint between the head restraint and the human head. And in the second test, we test for the seat-based sliding motion coupled with simultaneous deployment of the head restraint again by reducing the backrest distance. And to facilitate such tests, we had three scenarios. The first scenario is the fixed condition, the reference condition. And in the second scenario, we would simulate the reduced backrest distance. And in the third scenario, we would activate the sliding motion coupled with the reduction in the backrest distance. Now, the results in the first scenario provided us excessive rotation of the neck, resembles high potential of whiplash injury, and a maximum impact load acceleration of 5 times the gravity acceleration. The neck injury criterion calculated for this scenario was 8.2 meters squared per second squared. And as seen from the graph here, the point where the neck injury criterion is calculated is the point of rebound of the head, resembled by the red plot, at approximately 69 milliseconds. In the second scenario, we can see that deployment of the head restraint synchronizes the motion of the head and the torso, preventing excessive rotation of the neck. And if we take a closer look on the neck, we can see that the neck suffers no excessive rotation. The impact load acceleration remains the same. However, the neck injury criterion due to the synchronized acceleration was reduced to 5.46 meters squared per second squared. However, this time the rebound of the head, or the point where we calculated the injury criterion, was 59 milliseconds. In the last scenario, with the simultaneous activation of the sliding motion and the head restraint deployment, or reduction in the backrest distance, we can see that the head and the torso simultaneously have a synchronized motion throughout the duration of the impact. However, this time we can see that the impact load acceleration was reduced to a minimum value of 1.5 times the gravity acceleration, and the neck injury criterion was reduced to a minimum value of 2.2 meters squared per second squared, again with a rebound time, or the time of calculation of the injury criterion, at 69 milliseconds. With that, we're able to design and validate a whiplash injury prevention system, and also minimize the dynamic response of the human body during the impact. And with that, we were able to analyze the severity of the injury during different conditions. However, from our position, we can recommend for future improvement of such studies that we facilitate the tests for the changes in pressure of the fluid in the cervical, on the spinal cord or the spinal column, which would allow amendments to the current evaluation methods of the head restraints and the current injury criterion, which only depends on acceleration and forces, compression and tension forces on the spinal cord and the neck. I'll leave the final words to my colleague Abdullah Harris, so please.
So working on this project, we have learned many things. One of them is that mechanical engineering is not only limited to machines. We can deal with the human body through the gate of biomechanics. Also, we figured out the importance of solutions since the researcher couldn't reach their results using a real human body due to some limitations. Finally, I would like to advise myself and you to adjust your head restraint where the correct position is when the head restraint comes on the center of the human head, and try to keep the backrest distance as small as you can during the driving. and thank you.
Let's give the honors first to our, we have in the department somebody who had this accident quite recently. So let's give it the full question to Mr. Tausif. Dr. Tausif, rather. Thank you very much, John.
Okay, my first question is why the NIC units are in m square by s square?
Okay.
Can you back this slide?
You can tell me like that. So
Okay, it is the 0.2 is the relative or the average length of the human neck.
I mean to say why the units of neck injury are in m square divided by
So we have to
s.
go back to the equation.
Number 7.
No, you can just tell me without looking at the equation.
Okay, because we have acceleration, time, velocity, and 0.2 has a unit. It is meter.
No, it's not a times velocity.
It's acceleration additive to velocity, and the number 0.2 is the average length of human neck, which has a unit of
That's
meter.
fine. Why the units are in meter square divided by
Okay, I'll add
second
to
square.
what my colleagues have just said. The equation of the injury criterion is an empirical equation. This has been found through tests and simulations and crash tests using cadavers and volunteers.
My friend, why the units are in m
The
square
units-
divided by s square?
The units here are meaningless. It's an empirical
They are
equation.
meaningless.
I
They
believe
are-
this question, m square per second square, units of what?
Okay, it's a unit of the velocity squared,
And what is that? What is that? Units of what?
the whole equation itself is empirical. It was the results were found through crash tests and the development of such entry criterion is not our field of study. This equation is used as a tool.
My friend,
Okay.
look at the equation. What are the units of velocity?
That's meter per second.
Right.
Which is
so
square.
if you square,
Yeah,
it becomes
meters squared per second squared.
simple.
Yeah.
Where is imperial, empirical? No.
Just to clarify
Okay,
that
anyway,
why is
the
it
second question is, in your graphs,
Okay.
you were obtaining the values, these values.
Mhm.
I'm just curious how you are plotting these graphs, from where you were getting the values. And the second question is the same subsequent question. When you are going in your simulations, you were using finite element analysis,
Mhm.
right? Were you performing finite element analysis on the sliding component and the seat separately or together?
Okay. First of all, for the graphs, we obtain the results from the Elsteiner pre-post software in the post-analysis.
Which software, sorry?
Elsteiner pre-post. In the post-analysis section of the software, we can obtain graphs on the history of the acceleration in the x-acceleration direction, the history of that acceleration during the impact of the head and the torso, which is resembled by the T1 vertebrae. The graphs are obtained through the simulation software or the modeling software Elsteiner pre-post, which resembles the history of the x-acceleration of the head and the torso during the impact acceleration. Going to the second question.
The component
Okay.
of the seat.
The components of the seat and the slider. The finite element analysis is done on the seat as a whole, on the sliders and the seat.
Together or individually?
Sorry?
Together or individually? As one component or
Yeah,
individually?
it's as one component. However, the analysis of the simulation is not intended for the seat, it's intended for the head and the T1 vertebrae on the human body.
But I can see in your diagrams you
Yeah.
are using the seat as a finite element component as well.
Yes?
That's okay.
Let's have the question for Dr. Simon.
I'm just curious about what's the unique in the design of the head of the seat, different from what's existing now.
So, to facilitate the test of the head restraint deployment, we had either two scenarios. The first scenario is deploying the head restraint or reducing the backrest distance. So the unique of this head restraint, apart from the first scenario, which is the backrest distance, and you can see here.
Yeah, I understand. Like, based on what you increase the width of the...
Okay, based on the distance that the head restraint would deploy after the impact. So with the start of the impact, with the initiation of the impact, the head restraint would deploy to reduce the backrest distance to...
And you based on existing data, or...?
That was based on existing studies done by the International High Safety Institute and the National High Safety Institute in the USA, which recommend reducing the backrest distance. And this is also published by the Volvo, the WHIP system, the Whiplash Injury Prevention System, and Mercedes-Benz head restraint deployment.
Okay, thank you.
From Dr. Shilton.
Guys, just a quick note. You say design and validation. Validation, that means you are comparing the results towards another results.
Yes.
So when you do validation, even in the graph, in one of your graphs, you have to tell me how far you were from this. It's not just by qualitative saying that, you know, generally the two can...
Can we have Mr. Harris answer the question, please?
You need to tell me you're being far by 15%, 10%, you know, how much you're being far, because you're talking about validation. So validation, that means you're validating your results, which is numerical, against another results, which is either experimental or another work of somebody else. And then you tell me how far you are from that particular results. And it's not there. So the word validation there, a little bit misleading. Okay,
Thank you.
Dr. Sneedy? Very quick, as a matter of fact, in the same line. Well, I've noticed that you picked different schemes for your numerical grade, right? I mean, if you go to the other pictures, I mean, where is the grade? Where is the grade, right? The finite element grade. How did you come to this, that this grade will give you the best results? For example, did you do any refinement, a grade refinement study? If you change your grade, for example, if you refine it or you make it a little bit coarser, is that going to give you the same results, or the results going to be significantly different?
I think they have not done the finite element analysis as such.
Then how would we assess the accuracy of your results? Well, my point is the following, for this team and the previous as well. Let me just say this as a comment, because we are running out of time.
Excuse me, I think it's better to move to another, and then you can say it during the month, during the lunchtime, because time is overloaded.
I can quickly answer this.
Can you answer this question?
Yeah, quickly. So, quick answer. Okay. Quick answer to this is that for the best analysis during the finite element analysis, for the best results, we increased the mesh at the areas of which is more critical, which is the backrest of the seat and the head restraint, and also we increased the mesh to obtain better results and readings from the parts of the slider. The other parts of the seat are not intended in the study and thus have been left with larger or more bleak mesh, with a more larger mesh.
Thank you so much. We proceed to the next.